This lecture video will cover the valence bond theory or VBT. Please read the OER textbook chapter section 6.3 for more details. Pretty much in the previous chapter 6.1 video, we talk about the valence shell electron pair repulsion or VSEPR theory. We use that theory in order to predict the molecular geometry of the molecule. However, the VSEPR theory doesn't talk about how the bond exists between atoms. It just talks about the shape of the molecule. Therefore, there is the need of another theory to explain how the bond exists between atoms, and that is what we call the valence bond theory. Okay, so the valence bond theory will use the idea of the atomic orbitals of a specific atom, and we are going to combine those together to make the hybrid orbitals. We're going to talk about this in just a few slides here. And pretty much the VBT will be able to help us to understand the covalent bond better, and also will be able to relating this into the geometry that we learned from the Lewis structure and also the VSEPR theory as well. Okay, so there's some limitation as well that this theory will not be able to describe, and that's why there is another theory. There is a need of another theory to give us the full picture of the covalent bond, and that's what we're going to cover in chapter 6.4. Okay, so after you finish this lecture video, you should be able to start working on the paper homework 6.3. Okay, so pretty much is this part of chapter 6.3 right here. Okay, so number 1 to 6, that would be part of chapter 6.3. Okay, so let's take a look at chapter 5.1 first. When we talk about the formation of the covalent bond, right, so especially when we focus on the hydrogen molecule that contain 2 hydrogen atoms, right? So in order for covalent bond to be formed, these 2 orbitals, these 2 atomic orbital is the orbital of an atom, right? Of the 2 hydrogen atom will need to come close together. As they come close together, they will start to overlap, right? So at the optimal distance of the overlapping between the 2 atomic orbital, the electron will be able to share between that. Okay, so at this optimal overlap, at this point right here, the distance would be at the optimal distance as well, and we call this at this point the covalent bond. Okay, so the bond that determine between the 2 atoms is going to be measured at this point, and this is the point where the energy would be the lowest. Okay, so indicate that this is going to be the most stable state right here. Okay, so however, if you push these 2 atomic orbitals to get closer together, you will see that the energy will go up. It indicates that it starts to repel each other because it's going to be very unfavorable, because you have 2 nuclei that's getting closer together, and those nuclei will start to repel each other because they have the same charges, right? Positive charge nuclei. So pretty much what we're gonna look at is, in this theory, we're gonna look at how the valence bond theory explain this, right? Explain how these 2 come and overlap to form bonds. Okay, so that's what we're gonna take a look at. Okay, so before we looking at that, because the VBT focuses on the atomic orbitals, so you will need to understand the shape of the atomic orbital first. So this is recall from the previous chapter when we talk about the angular momentum number, right, that describe the shape of orbital. So in this case, we're gonna looking at both principal quantum number and also the angular momentum number as well. So the first number, this number right here that come before alphabet. Okay, so again, to recall from what we learned earlier, these numbers show the number of energy shells, right, the main energy shells, which is the principal quantum number n. Okay, the letter that you see S, P, right, those are going to be described by the angular momentum number, which is L, right? So it's the sub energy shell. Okay, so for example, the number that related to this when L equal to 0 would be S, right? When L equal to 1, that would be P. When L equal to 2, right, that would be D. And when L equal to 3, that would be F, right? So that's what from what we learned previously. And again, number of n would be the number of shells, that the main energy shells that we would see in the Bohr's model, right? For example, if you have nucleus, n equal to 1 would represent the closest energy shells that closest to the nucleus, right? This would be n equal to 2 and so on, right? So that's what the n tell us. So now the picture of the atomic orbitals would be related to that, right? Would be related to the shape of these and how big they are. Okay, so let's take a look at what would be the first one. Okay, so 1s orbital would be a sphere, like a spherical. So it's going to look like this. Okay, 2s, because the shape of s are going to be the same, so it's going to be a sphere shape as well, but because to indicate the number of energy shells, right? So that means between 1 and 2 would be bigger because it's further away from the nucleus. So in this case, it's going to look the same, except it's going to be bigger, right? When we talk about 2p, okay, so p, the picture of the p orbital would be the dumbbell. Okay, so p subscript x is going to be along x-axis. Okay, p subscript y would be along the y-axis. P subscript z would be along z-axis. Okay, so these x, y, and z tell you about the number of magnetic quantum number m sub l, right? Because if you think about this, because we have L equal to 1, which is represent p orbital, therefore the value of m sub L would be negative 1, 0, and 1. And this m sub L value represent different orientation along x, y, and z axis. So pretty much what I would like you to focus on are these two subatomic orbital, s and p. Okay, so you're going to see this along the whole lecture when we talk about the combination of all of those. Okay, so and also this picture here will also help you to answer the problem on the homework as well. All right, so let's take a look at how we can overlap atomic orbitals. Okay, so remember, like, this is the picture that we are going to look at. Okay, so we're going to use this atomic orbital. It's depend on what I'm talking about, right? So when I talk about p, you will need to know it's going to look like this, right? When I talk about s, you know it's going to look like this. Okay, so let's take a look at the overlapping of orbitals that come from the atomic orbitals of hydrogen first. Okay, so two hydrogen come together. And this type of overlap I'm going to call is head-to-head overlap. Okay, so what do we mean by that? Okay, so head-to-head overlap. So pretty much the atomic orbital of hydrogen, if you write the electron configuration of hydrogen would be 1s1, right? Same thing for the second hydrogen as well that they are going to form the bond with. Okay, so it's going to also be 1s1 as well. And the atomic orbital, because it's in s, so therefore it's going to be a spherical shape. Okay, so 1s1, 1 represents the number of electron, right? So we have 1 electron on each. Okay, for the atom to be able to overlap, the direction of the spin of the electron must be the opposite, right? So because they are going to have to come and pair up together. If they are on the same side, then they are going to repel each other. So therefore, in this case, these two are going to be on the opposite side. So that when you overlap, or we do head-to-head overlap, so look at this as a head, right? You're pushing them together. These two come close together. You push them together. You are going to end up with these two are sharing the space of their electron. This sharing space of electron, that's what we call overlapping, right? So this overlapping right here is going to indicate that the two electrons from each atom will come paired up in the same orbitals. These same orbitals right here, we call this the sigma bond. Okay, so sigma bond is the single bond that contain two electrons are sharing the same space. Okay, so this is the head-to-head overlap, and that single bond right there. That's what represents the sigma bond. Okay, so again, sigma bond represents single bond. Okay, so it's indicate the bond that come from the overlapping of the two orbital that two electrons are sharing electron within that region. Okay, so it's come from head-to-head overlap. Okay, so what about the sigma bond that come from, let's say, the hydrogen and fluorine? Would that be the same as what we see earlier? Okay, so you already see the atomic orbitals of hydrogen, which is 1s1, right? So it looks like that. Now, what about fluorine? Okay, so fluorine, if you look up the electron configuration, you will see the electron configuration of fluorine contain helium and then 2s2 and 2p5. Note that 2s2 is already occupied, is fully occupied because the 2s orbital can contain maximum of 2 electrons and is already occupied. Therefore, you cannot use the 2s to overlap. However, if you're looking at 2p, right, so 2p contain 3 orbitals and you have 5 electrons, so 1, 2, 3, 4, 5, you will see that the 2p5 one of the 2p right here, right? So this is one of the 2p, okay, is contain only one single electron that you can use to overlap. Okay, so in this case, I'm going to do that. Okay, so this is the only one that can be used to overlap, because when you overlap two atomic orbitals, they need to form bonds, which mean that those orbitals need to have an empty space for the other or for the incoming electron to share space with, right? So that means in this case, this is the only one that we can use to share the electron with the hydrogen. Okay, so because this one is belong to 2p, therefore the picture of the atomic orbital we're gonna draw here is going to be the P shape, which is going to be the dumbbell. So now the question is, how do I know it's going to be along x-axis, y-axis, or z-axis? So that is when you are going to look at how you want to overlap them. So in this case, we are going to look at head-to-head overlap, which means that you are going to focus on the head of the orbital. So in this case, it would be, we're going to use 2px because these are the head of the orbital. Right, so we're gonna use the head of orbital. So that would be one electron, right, that come from 2px here, that is going to be overlapped with 1s of the hydrogen. If you overlap them, you push them close together, right? So this would be head-to-head overlap. Okay, so you are sharing the same space of these two electrons, right? Sharing the same space. This is going to be the bond that created between hydrogen and fluorine. Okay, so that's what this bond is look like. Right, and this bond right here, because it come from head-to-head overlap, this bond is considered to be sigma bond. Okay, so this sigma bond is represent the single bond, okay, between the two atoms. All right, now what about if you have p orbitals? Both of them are p. For example, fluorine and fluorine atom come together. As I mentioned before, the only orbital fluorine can use, right, would be the 2p. Therefore, I'm going to use 2px in this case. The reason for that, because I'm going to do the head-to-head overlap. These are the head of the orbitals. I'm going to overlap these two head. Okay. So if I overlap that, it's going to look like this, right? Because these two come together to share the same space. Okay, so the electron density will be able to find the most condensed around here, right, between the two nuclei. They are going to share the electron between these two, between this region here. So again, because we have head-to-head overlap, the bond of this would be a single bond that is called sigma bond. Okay, so again, sigma bond represents single bond, and sigma bond come from head-to-head overlap. Okay. So we already have used, so far you see the s and s orbital overlaps, s and p orbital overlap, and also p and p orbital overlap through the head-to-head overlap, right? The final overlapping type that I'm going to focus on is going to be side-to-side overlap that is going to make the pi bond. What do we mean by that? What is pi bond? Okay, so that's what we're going to take a look at. Okay, so I'm going to use the leftover 2py. Okay, so when you have 2py, the p orbital would be along the y-axis. When you push these two close together, because these are the head, you are not directly have head-to-head collide, right? You actually do the side, right? This is its side of the p orbital. You are pushing the side to be close together, so that's why we call this side-to-side overlap. If you do side-to-side overlap, the picture that you are going to get is going to look like this, right? So these two are going to share space between these two, which is outside the nuclei axis, right? So it's actually on between these two loops. Okay, so more correctly, right, you are going to see this as, you know, like they kind of like merge together around this region, right? So that's what you're gonna see it as. You can represent it as like this, that you just overlap them, or pretty much know that this whole region is going to be shared, those electrons between the two atomic orbitals. Okay, this bond right here we call pi bond. Okay, pi bond is part of double bond and or triple bond. Okay, so I'm going to talk about that later. Whenever that you see double bond and triple bond, know that it's going to contain pi bond as well. Okay, it's also going to contain sigma bond as well, and I'm going to talk about that later. Okay, so another way to create pi bond is do side-to-side overlap of 2pz. Okay, because if you're looking at this, right, 2pz, when you move these two together, side to side overlap, you are going to create that type of picture, right? Oops, sorry, that type of picture right there, right? Which is going to be pretty much this picture, but you like tilt it along the z-axis, right? So this is represent pi bond. Okay, so pi bond come from side to side overlap. So let me summarize this again. Okay, so sigma bond come from head to head overlap. Pi bond come from side to side overlap. Sigma bond would be part of the single bond, and pi bond would be part of the double bond. Okay, so we're gonna take a look, and also triple bond as well. Okay, so here's the summary of it. Okay, so PX overlap would make sigma bond, PY or PZ overlap would make pi bond. Okay, so the sigma bond is much stronger than the pi bond. The reason for that is because when you're looking at the electron that are sharing, is sharing between the two nuclei, right? So that means in this case, it would be stronger because the interaction between nucleus positive, negative, positive are much stronger than when it's out of plane, right? So this is these two electrons are sharing, but it's outer plane of the two nuclei. So it's making the double pi bond would be a little bit weaker. Okay, so pi bond. Again, I did not use the word double bond or single bond in this case because eventually you will see that the double bond would contain sigma bond and pi bond. Triple bond would contain sigma bond and 2 pi bond. We're going to talk about that later. Okay, so now let's take a look at an atom like carbon and see how carbon can actually form 4 bonds. Okay, so I'm going to start with the electron configuration of carbon, which is start with helium, 2s2 and 2p2. If you draw this, you will see that it contains 4 valence, right? So, and if you draw the orbital filling diagrams, we see that all of these would already occupy, right? So 2 from the inner core and 2 from the 2s is already occupied. The only electron that are unpaired is going to be in 2p, so 1 and 2. So that means that if you're looking at this, carbon can only form 2 bonds, right? Because it's contain only it's contain only 2 available electron that can fill an extra, right? So an extra orbital, extra electron can be filled in these 2, right? So that means maximum carbon should be able to create bond should be only 2, but that's not true because carbon can form 4 bonds, not only 2 bonds. According to the Lewis structure that we see earlier, carbon can form 4 bonds. And those 4 bonds, how is it possible then, since we have only 2 electrons unpaired that can overlap, right, that can be used to overlap? If you go back from the previous slide, you will see that, for example, fluorine, you will need to use the atomic orbital that contain only 1 unpaired electron to overlap. Anything that occupied by 2 electrons, you will not be able to use those. So how come this one you can actually form 4 bonds then, since we have only 2 electrons that can actually overlap, right, with another atom? So the answer to this is going to stem from the hybridization. Okay, so what is hybridization? Hybridization is a process in which the atomic orbitals mix to form new orbitals called hybrid orbitals that allow them to form or overlap their hybrid orbital with other atoms. Okay, so what do I mean by that? Okay, so let's take a look at the first type of valence bond theory of the hybridization. Okay, so sp3. So what is it? Okay, so I'm going to use carbon steel. Okay, so I'm going to plot energy diagram. Okay, so this is the energy going up. Okay, so indicate energy going up. Lower would be indicate lower energy. Higher state would be higher energy. So if you look at the standard atomic orbital of carbon, I'm going to look at only the valence electron. Okay, so I'm going to start with 2s2 and I'm going to start with 2p. Okay, so we already see that carbon contains 2 electrons in the 2s and 2 electrons in the 2p. And these energy level of the 2s and 2p would be slightly different, right? Because 2s would be closer to the nucleus than the 2p. Okay, but they are still reside in the main energy shell too. Okay, so these are the sub shells. Okay, so So that means in this case, that's why I split them, because this is going to be slightly higher because 2p is further a little bit, what do you call, like has higher energy than 2s. Okay. When you are going to mix this, right, because the hybridization means you are going to mix them, right, it's the process of mixing them. This process of hybridization is going to mix whatever available, right? So in this case, because we are going to make the hybridization called sp3, S indicate that you are going to need to use one of the s orbital, and superscript 3 tell us that you need 3 atomic orbital that come from p. Okay, so that means in this case, I'm going to have to use all of this, right? So one come from the 2s, s orbital come from the 2s, and p orbital come from 3 of these 2p orbitals. We're gonna mix all of that together. Okay, so we're gonna use all of that. If you mix these, you are going to get the average hybrid orbital, right? So hybrid means the average orbital. The average of these will come out, right? So you add 1 of the 2s and 3 of the 2p. Total number of orbitals would come out to be the same, right? So you have 1, 2, 3, 4. You start with using 4 atomic orbitals. The result orbitals have to be the same. The result of orbital come out to be 4 as well, right? So you start with 1, 2, 3, 4. The result also going to come out equal to 4, 1, 2, 3, 4. But these 4 atomic orbitals, we do not call these 2s or 2p anymore, because you mix them. You mix them together. Therefore, these, the name of this would be the average of these two, right? So we call the new name of these hybrid orbitals. And the name of this hybrid orbital is called sp3. This one is called sp3. This one is called sp3. This one also called sp3. This is also sp3. Okay, so we have 4 sp3 hybrid orbitals that stem from mixing of the s and the p. Okay. Now, how can carbon form 4 bonds then? That's when you will need to start to filling the electron that we start with into these hybrid orbitals. We start the electron with 4, right? Carbon contains 4 valence electron. We are going to use those 4 valence electron and fill into this new hybrid orbital. 1, 2, 3, 4. We're gonna fill those 4 into here. So fill 1, 2, 3, 4. You're gonna fill those. Okay, so pretty much again, the hybrid orbitals would have the energy between these two because the average. Okay, so and you are going to be able to now use this one single electron to overlap with an incoming atomic orbitals. Okay, so the electron that reside in the hybrid orbitals is going to form sigma bond. Okay, so these are going to be the part that is going to when it's undergo overlapping, it's going to be head-to-head overlap. It's going to form sigma bond. Okay, so so all of this would form sigma bond. Therefore, carbon can form 4 sigma bond or 4 single bond. Okay, it's come from that. Okay, the hybrid orbitals minimize the energy of the molecule by maximizing the orbital overlap in the bond. Okay, so let's take a look at a molecule that contains 4 sigma bond here. Okay, so that molecule would be, for example, okay, so I have a picture here. So if you have all of these, right, you mix them together, the picture of the hybrid orbitals is going to look like somewhat between here, right? So you average them. So it's gonna look like this, right? So pretty much this represents sp3. Okay, so this is also represent sp3 as well. This is also represent sp3. Okay, so I think my slide here is shift a little bit. Okay, so I'm going to have to indicate this is sp3, this is sp3, this is also sp3, and since we have 4 of them, the last one also sp3 as well. Okay, so I want you to ignore, so there is some error on the slide. Okay, so again, so we have S and P mixed. If you use 1s and 3p, you're gonna end up with sp3 hybrid orbitals, and each of these going to represent different orientation, right? So this is along this corner, this is along this corner, this is along that corner, and this is like up, right? So these, if you combine them together, if you combine all of these 4 sp3, you are going to get the picture that look like this, right? So if you measure the bond angle between here and here, it's come out to be 109.5, which is going to be the same as tetrahedral, right? So this is the tetrahedral geometry. So if you look at carbon, right? So we're looking at carbon here. Okay, so this is the atomic of carbon. This is the carbon. So these single electron that are in the hybrid orbitals, right, that are in each of these, then going to be able to overlap with another atom. For example, in this case would be hydrogen, right? So those going to overlap with the hydrogen, so they are going to share electron together, head-to-head overlap. That's what we look. That's what we see as sigma bond, right? So all of these single bond represent sigma bond. Okay, so that means in this case, when you have sp3 hybridization, note that you are going to associate with this with the VSEPR theory as tetrahedral. Okay, so whenever you see tetrahedral geometry, right, so it's going to have this sp3 hybridization. Okay, it's come from that. All right, so the next one is sp2. So instead of mixing all 3p orbitals available, we're going to use only 2p. Okay, so an example of this same thing, I'm going to use carbon the same. Okay, so we're going to start with the same atomic orbital, which is 2s and 2p for the valence electron in the carbon. Okay, so what I'm going to do is I'm going to mix, but in this case, we are going to mix only s and 2 of the p orbitals. Okay, so I'm going to choose only this. Okay, if I mix only this, note that I'm mixing only 1, 2, 3. Therefore, the result of the hybrid orbital would be 3, right? 1, 2, 3 is come from mixing this one, and this one. Okay, so mixing those. Okay, these hybrid orbitals now is going to be called sp2. You are going to end up with 3 sp2 because you are mixing 1 of the 2s and 2 of the 2p. Total would be 3, and the new name would be sp2 because s indicate you use 1 of the s and p indicate you use 2 of the p. Okay. Again, the energy of the hybrid orbital would come out to be the average between those that you mix. Okay. So now, what do you do with the one that did not undergo mixing? You still need to include that. Okay, because whatever that you start with is come out have to be the same, right? You're mixing 3 orbitals, the result has 3. The one that did not undergo mixing or did not undergo hybridization is going to stay the same. Okay, so now when you filled out the electron, you are going to use the number of electrons that you have originally, which are 4 of them, right? You're going to start to fill off these. How do you fill this? Okay, so how do you fill this is you are going to fill all the way on the bottom part and go up to the one that is, what do you call it, that is empty as well. So the reason for that is because once these two are mixing, okay, so the energy of these is going to be a little bit closer to this one, allowing for the electron to be able to jump to that. Okay, so in this case, this orbital right here is called unhybridized p orbital because this p orbital did not undergo hybridization. Okay, so this is called unhybridized. This is called hybrid orbitals. So when you fill electron, you are going to fill all 3 on the bottom and then go up 1 more. The reason for that, again, these two energy are very close to each other, so it's not much different. So that's why it can allow 1 electron to go up there. Okay, so what type of bond it would be created from this? Again, the electrons in the hybrid orbitals always going to make sigma bond. Okay, so all of these represent sigma bond, which means they are going to use these electron right here to do head-to-head overlap with another atom, right? The unhybridization of the p orbitals always going to make pi bond, which means that whatever left in the pi here will not be able to use head-to-head overlap, but it will use side-to-side overlap to form pi bond. Okay, so there will be a picture that is clearer in explaining this. Okay, so let's take a look at picture here. So pretty much, again, so the representation of this picture of S and P would be those, right? So we are going to use only these two. Okay, so we use PX and PY, okay, and S. So what you are going to end up with is you are going to end up with 1, 2, 3, right? So you're going to end up with 3 hybrid orbitals. And these are 3 hybrid orbitals, which is going to be in a different orientation, right? So each of these tell you about different orientation. And these are what we call SP2, right? So this is what we call SP2, okay? If you combine all of these together, or if you show them together, okay, show 1, 2, 3, show all of these together, you are going to see that this is going to be 120 degrees away from each other. So if you look at this and recall or tie it back with the VSEPR theory, so when you have the bond angle 120 degree, right, this is going to be what? Trigonal planar. So that means whenever that you see trigonal planar, it's going to tie back into sp2 hybridization. Okay, so pretty much each of these, because it contains one electron, right? So it can use this one electron right here that come from this, okay, to overlap with another by head-to-head overlap. An example of that would be two hydrogen, right? For example, in this case, so I'm going to focus on here, right? So that's the carbon that we are looking at, which contain three hybrid orbitals. Okay, so three hybrid orbital, 1, 2, and 3. These three hybrid orbital is going to overlap with another atom. So in this case, going to overlap with hydrogen, forming sigma bond. Okay, overlap with another another hydrogen, forming sigma bond, and it's going to overlap head to head as well, right? This head right here is going to overlap with oxygen head. Okay, so oxygen has p orbital, and forming sigma bond as well. Okay, so that means in this case, we have sigma bond here, we also have sigma bond here, we also contain sigma bond here. But because we also have the unhybridized p orbitals, this unhybridized p orbital would form pi bonds, and that is what is represented here, right? This is the unhybridized p orbital that is going to come together and overlap with another side to side to form pi bond, right? So that's why you are going to see pi bond in this as well. Therefore, in this case, when you see double bond, it's going to contain both sigma bond and also pi bond as well, right? So that means in this case, I can conclude that this one double bond here contain both sigma bond and also pi bond. Okay, so it's come from that. All right. So when we talk about single bond versus pi bond and or double bond, note that there is some rotation that is actually involved with this. When we talk about single bond, you see that the bond between the two atoms are going to be through sigma bond, right? These are sharing electron together. Pretty much if you want, you can rotate this, right? So you can like flip this around. Okay, so you can rotate that. There is no restriction for that. It's freely rotate. Okay. However, when you talk about double bond and triple bond, the presence of pi bond in double bond and triple bond prevent the rotation of the molecule. So that means in this case, you will not be able to rotate this at all. You will not be able to twist this. It fixed together in this one orientation. Okay, so I will have a separate video to show you that. Okay, so look for that. All right, so the next hybridization is sp. Okay, so the next hybridization is sp. I'm going to use the same atom again for the easiest for us to understand. So carbon start with the same type of atomic orbitals, the same. Okay, so 2s and 2p. And what I'm going to mix here, I'm going to mix just one of the S and one of the P. So that means I'm going to use only these two, right? So one of the 2S, one of the 2P. So therefore, if you mix these two, the result would be how many orbitals? 1, 2, it would be 2, right? So the result of mixing these would be the average of these two, which is going to come out equal to 2 orbitals. These would be the hybrid orbitals that is called sp. So this is the two of the sp hybrid orbitals that come from mixing these two, right? You add these two up, 1, 2. Okay, so each of these is sp. So what do you do with these two? Well, as we mentioned earlier, right? So you're gonna have to have that leftover, right, on unhybridized. Okay, so this would be the unhybridized p orbital that come from these two. So again, the next thing you're gonna do is you are going to use those 4 electrons from what we have from carbon and start to fill into here, right? So 1, 2, 3, 4, right? So again, those single electron in the hybrid orbitals, in these hybrid orbitals here, going to be the one that form sigma bond, okay? And those that are in the unhybridized p orbitals would form pi bond. Okay, so note that. Okay, so now let's take a look at what would that look like. Okay, so if you mix these two, right, if you mix these two together, you are going to end up with the two orientation. One look like this, the other look like this, right? So it's represent these two. Okay, if you show these two together, okay, so it's look like so it's 100 degree away from each other. So this is going to related to linear geometry. Okay, so now what does it mean, right? So if you put this into the molecule that contain carbon-carbon triple bond like this, you will see that the sigma bond would form between one is, so this one right here is going to overlap with one hydrogen, right, to form sigma bond. So this is sigma bond right here. Okay, the other one, right, so the other one, okay, going to be used to also overlap to another carbon, okay, form another sigma bond. So that means in this case, this triple bond right here also contains sigma bond. Okay, because we already used those hybrid orbitals, right, that to form sigma bond, the leftover, which is these two, would be the leftover of 2py and 2pz that we did not mention earlier. And because we have 2py and 2pz left unhybridized, these two are going to do side-to-side overlap, right? This is unhybridized. They are going to do side-to-side overlap, forming pi bonds. Okay, so that means in this case, if you're looking at triple bond would contain sigma bond plus 2 pi bond, because the 2 pi bond come from this unhybridized p orbital, 2py and 2pz. Okay, so you are going to see similar example later. I'm going to walk you through more example of how to do this, and my expectation is you should be able to complete the homework as well by using this idea. Okay, so let's take a look at the next one. What if I look at, so we already see the linear, trigonal, planar, and tetrahedral. What about the other two geometry that we have not talked about, right? So that's what we're going to take a look at. Okay, so when you have more than 4 electron domains, if you have 5 electron domains or 6 electron domains, you will need to use the d orbital as well, because if you use only s and p, you are going to end up with only 4 bonds, right, or 4 region of the electron. In order to increase to 5, it will need to involve with d. So if it's involved with d, this would be called sp3d, because you use one of the s, 3 of the p, and 1 of the d. If you mix this together, these are going to result in 5 sp3d hybrid orbitals, and the leftover would be the unhybridized d orbital. Okay, so pretty much you don't need to know this how this work, but what I would like you to focus on this slide is that note that the sp3d would represent trigonal bipyramidal. Okay, because after you mix all these S, P, and D together, it's going to create this trigonal bipyramidal geometry from the 5 different orientation of the hybrid orbitals sp3d. Okay, so for example of that would be arsenic pentafluoride, right? So if you put this together, right, so this is going to be the hybrid orbital that we talked about earlier, and fluorine would use its p orbital to overlap, right? So that's why the picture is look like this. Okay. All right, so what about octahedral then? Well, octahedral requires 6 electron domains. Therefore, you will need to include one more of the d orbital. So this one right here should be sp3d2. Okay, can you correct this for me, please? Should be sp3d2. Okay, so if you mix them together, it's going to result in 6 hybrid orbitals, because you mix 1, 2, 3, 4, 5, 6, right? So you end up with 6 hybrid orbitals, and it's going to, if you overlap all of these together, show them together, it's going to come out to be octahedral. Again, so this is sp3d2. Okay, so an example of this would be sulfur hexafluoride, right? So it's going to represent by this, right? So this is the sp2 hybridization. Okay, that when you show off these 6 hybrid orbitals together, it's going to represent those 6 electron domain region that can head-to-head overlap with another atom. So in this case would be fluorine. Okay, so my summary for this is that when you have the linear electron domain geometry, know that the type of hybridization would be sp. okay, because linear has only 2 electron group, right? So you're going to use one from S, one from P, okay? The rest of that would form, you know, like the pi bond, right? And when you have 3 electron groups, that is going to form trigonal planar, right? So in order to relate it to hybridization, you need to use one from the S, two from the P, 2p, right? Add together, you're going to end up with 3 electron region, so 1, 2, 3, right? So that would represent the this carbon right here with the double bond here. So that means going to form 3 sigma bond, right? It will be able to form 3 sigma bond, and the leftover p orbital would be forming the pi bonds, okay? If you have 4 electron domain groups, right, you are going to have the tetrahedral as electron domain geometry, and the hybridization would be sp3, because to have 4 electron groups, you need one of the S, 3 of the P together to have 4 electron domains, and that would represent single bond for all of these, which is the sigma bond, okay? So my expectation is you will need to be able to draw the diagram of the mixing or of the hybridization for this. Last two, okay, so pretty much last two, you don't need to be able to draw the diagram, but you will need to be able to relate it, the electron domain geometry, to the hybridization. Okay, so trigonal bipyramidal would be sp3d, octahedral would be sp3d2. Okay, so now let's take a look at example. Okay, so we already see the theory. So now how can we actually apply that? Okay, so I have these 2 molecules together, so I'm going to walk you one by one. Okay, so example 1 is to determine the hybridization of the assigned atom in the following molecules and total number of sigma bond pi bonds. Okay, so in order to do that, first you will need to make sure that you actually have the correct Lewis structure, which means you will need to make sure you have all the electron pairs filling. Okay, so if you're looking at the first molecule here, you will need to count the number of valence, right, which is 5 from phosphorus and 7 from each chlorine, right? So 3 of them total would be 26. If you're looking at this molecule, okay, so we already spent 6 electrons in bonding, right? So 1, 2, 3, 4, 5, 6. You're missing 20 more. Okay, so because you're missing 20 more, you are going to distribute these into the outer atom first to make sure that each of those can have an octet, right? So octet, octet, octet. And then the leftover would be put in the central atom, okay, which is the phosphorus right now. So the reason why we need to do this, because we need to determine the correct geometry, because the electron domain geometry will help us determine the type of hybridization. As we see earlier, right? So for example, linear would be SP, right? Trigonal planar would be SP2. Tetrahedral would be SP3, right? Trigonal bipyramidal would be SP3D. Octahedral would be SP3D2. Therefore, in this case, in order to know the correct electron domains, it would tell you the correct type of hybridization. So that means in this case for phosphorus, if you're looking at this, right? So phosphorus contain 1, 2, 3, 4 electron groups. Therefore, the type of hybridization would be sp3, right? Because 4 electron group need to contain 4 electron region, and those 4 electron region is going to come from the mixing between 1 of the S, 3 of the P together would equal to 4, right? Therefore, in this case, if you're looking at the number of sigma bond would represent the single bond. So 1, 2, 3 is going to contain only 3 sigma bond. Is there any pi bond? The reason, the answer is no, right? So pi bond would be 0 because pi bond only exists in double bond and triple bond only. So wait a second. So since we have 3 electron domain, we have only 3 sigma bond though. So what is the fourth one? Well, the fourth one is the region of the lone pair that occupy. Okay, so that means in this case, one of the hybrid orbital would contain lone pair. That's what it tells us. Okay. Now the second example, okay, would be this molecule right here. So carbon, okay, so same thing, right? So is it already what is the correct Lewis structure of this, right? So pretty much you are going to do the same thing, right? So total would be 12 valence electron. Okay, so we already spent 8 in bonding, 1, 2, 3, 4, 5, 6, 7, 8. So that means left over would be 4. carbon already has an octet, hydrogen is already has a duet. So that means those 4 electrons would go to oxygen. Okay, so now, but the problem asking for or focusing on only carbon, not oxygen. So we're going to look at carbon. Carbon contain how many electron domain? The answer is 1, 2, and 3, right? Because double bond count as 1. Okay, so we have 3 regions of carbon, 3 electron regions. Therefore, the hybridization would be sp2 because 3 electron region coming from the mixing of orbital of 1 of the s and 2 of the p. Total would be 3 electron domain. Okay, so 3 electron domains, how many sigma bond is contained? You are going to count sigma bond from the single bond, right? So this contains sigma bond, this also contains sigma bond. Double bond also contains sigma bond as well, and also contain what? Oops, sorry. So this contains sigma bond and also contain pi bond as well, right? 1 pi bond. Double bond contains 1 sigma and 1 pi. Therefore, in this case, the total number of sigma bond around this carbon would be 1, 2, 3, right? And then the number of pi bond would be 1 that is coming from the part of the double bond. Okay, so that would be an example that you are going to do on the paper homework. Okay, so now let's take a look at the next example. This example here, I would like you to pause the video now and attempt what I mentioned to you earlier. Okay, so pretty much pause the video now to see how will you actually understand the lecture. Okay, so if you are not able to do this at all, it just means that you don't actually fully understand it. Now let's check your answer. Okay, so in order to determine the hybridization of an acyl atom, first you will need to know the electron domain geometry of that atom first. So in this case, in order to determine the electron domain geometry of all of these, you will need to make sure that you are having the correct Lewis dot structure by filling all those lone pair. Okay, so pretty much in this case, if you're looking at this, right, C and then have the 3 hydrogen, this is called a condensed part. This is not a fully correct Lewis structure yet. It just tells you like a short term of the Lewis structure. So in order to help us determine this correctly, what you will need to do is just make sure that extend those into a bond, right? So which pretty much just means that carbon is actually connected to 3 hydrogen. That's what it means. And this molecule missing a lone pair on nitrogen here. Okay, so again, how do you determine that? Just using the number of total valence electron and then find out how many electron you will need for the nitrogen, right? So that's how I do it. So that means in this case, the carbon of this carbon here that connected to 3 hydrogen would have the tetrahedral electron domain geometry, which is 4 electron domain. Okay, 4 electron domain, the hybridization that associated with 4 electron domain would be sp3, right? Because 1 come from the mixing of s and the other 3 come from the p, so total would be 4. Okay, so carbon in the middle contain only 2 electron domain. Okay, so 1, 2, triple bond count as 1 region, so that's why we count this as 1. So therefore, carbon here contain only 2 electron domain. Therefore, the electron domain geometry would be linear. Okay, so because linear is going to be is contain 2 electron domain, therefore the hybridization associated with this would be just 1 of s and 1 of p, right? So it would be sp. Now this hydrogen right here contain 2 electron domain also. 1 come from triple bond, the other come from lone pair. Okay, electron domains count all the electrons, right? And also the single bond and triple bond as well. So 2 electron domain, therefore the hybridization would be also sp. Okay, total number of sigma bond, how many? Okay, so sigma bond contain in single bond and also pi bond, also triple bond as well. So if you count number of sigma bond, this is going to contain 1 sigma bond, right? 2 sigma bond, 3 sigma bond, 4 and 5. So total of sigma bond would be 5. What about pi bond? Remember, pi bond are part of double bond and triple bond. In double bond, there is 1 pi bond. In triple bond, there are 2 pi bond. So in this case, there are 2 pi bond that is composed of this triple bond. So again, so in summary, this triple bond right here contain 1 sigma plus 2 pi. Okay. The next one, same thing. Okay, so you will need to actually complete the correct Lewis structure by adding all of those lone pair first. Okay, and then it will give you the correct answer for the hybridization. The oxygen with the double bond. Okay, so this oxygen right here contain 1, 2, 3 electron region. Therefore, the hybridization would be sp2, right? Because we need 3 electron regions, so 1 from s and 2 from p orbital. Total would be 3. This oxygen here with the single bond contain 1, 2, 3, 4. 4 electron domains would be tetrahedral, right? So the hybridization would be sp3. Okay, so again, you are going to determine the hybridization from the correct Lewis structure and by looking at how many electron domains you around that atoms, right? And then related that to the hybridization. How many sigma bond for this whole molecule then, right? It said total, right? So it's going to be total for the whole molecule. It's going to be what? 1, 2, 3, 4, 5, 6, 7, right? Because each of those contains sigma bond. Okay, so single bond contain 1 sigma bond, double bond contain 1 sigma bond, so total would be 7. And number of pi bond going to present in only double bond or triple bond. So in this case, this molecule has double bond, so therefore that will be 1 pi bond. Okay, so you will see more example of these in the paper homework, chapter 6.3 to 6.4. Okay, so please start working on those so that way you can reinforce your understanding. The next part of my expectation is you will need to also be able to draw the diagrams that represent hybridization as well. Okay, so we're gonna actually practice this. Okay, so that would be my expectation. Okay, we are going to use the scenario that you already see with the carbon earlier that I show you with the atomic orbitals and how you can mix them, right? So we're gonna look at that. Okay, so but the molecule we are going to look at today is going to be water. Okay, so different central atom, right? So before you look at central atom of carbon, now we're gonna focus on a different atom now, which is oxygen in this case. In order for us to draw the diagrams, okay, that represent hybridization, first you will need to be able to predict the correct hybridization of oxygen first, because without doing this correctly, everything else will be incorrect. Okay, what should be the hybridization of oxygen here? That's when you first will need to look at their correct Lewis structure, right? Is this correct Lewis structure yet? The answer is no, because missing lone pair, right? So if you count the number of valence, you will see that you spend only 4 electron in bonding. You're still missing 4, and those 4 would be part of the lone pairs. Okay, by knowing the lone pair, knowing the number of bonds, you are going to be able to find out the number of electron domain geometry. This contains 4 electron domains. Therefore, this is going to be related to tetrahedral. Okay, and because it's tetrahedral, therefore the hybridization of this molecule would be sp3, right? Because 4 electron domains is going to require the overlapping of 4 hybrid orbitals come from sp and 3 of the p mixed together. Okay, because we are going to make sp3 hybrid orbitals, so what we're gonna need is that we are going to need the atomic orbitals of oxygen. Okay, so if you recall from the electron configuration of oxygen, you are going to see that, you are going to see that atomic orbitals of oxygen would contain 2s, right? This is of the valence electron. Okay, so we are focusing on only the valence electron. Valence electron of oxygen resides in 2s, okay, and 2p. Okay, 1, 2, 3. And because total of the valence electron of oxygen equal to 6, right? So that means in this case, you're going to have 1, 2, 3, 4, 5, 6. You have total of 6 valence electron in the atomic orbital of oxygen. Okay, so this is going to be 2p. Of this orbital are 2p. So again, how did I get this? Again, it's coming from the electron configuration of oxygen. Okay, we are focusing on only the valence electron. Therefore, in this case, the valence electron that we are going to consider would be in the 2s and in the 2p. Okay, so total would be 6 electron total. All right, now we are going to do the hybridization similar to what we did earlier with the carbon, and we are going to mix what are we going to mix? Okay, so we're gonna mix all of this, right? We're gonna mix s and we're gonna mix p orbitals. We're gonna use one of the s and we're gonna use three of the p. Therefore, in this case, if I'm going to mix, I'm going to have to mix all of this together. Okay, if you mix all of these together, the result of the hybrid orbital would be 1, 2, 3, 4, right? Because you mix all four. Therefore, the new hybrid orbital would be, the energy would be in the middle of this. So it contains 1, 2, 3, 4, right? These four hybrid orbitals have a new name now because you're mixing them together is the average of those. This new name is what we call sp3, right? So this is what we call sp3. Okay, so all of these are sp3, but in different orientation as you see earlier. And when you combine them together, when you show them all together in those different orientation, is what come out to be as tetrahedral, right? Is there any unhybridized? The answer is no. There is no unhybridized because you actually use it all, right? So the next thing is you will need to actually fill in the number, you will need to fill in the electrons that you have, right? So oxygen here contain 1, 2, 3, 4, 5, 6 electrons. Therefore, you're going to use those 6 electrons to fill into these hybrid orbitals, right? Because it's going to come together. You're not only mixing the atomic orbitals, you also need to carry those electron with it as well. So I'm going to start to fill those 6 electrons. Okay, so again, you're going to base off the rules that we learned earlier, right? So you're going to fill we fill this first, right? So 4 and then 5, 6, you start to pair them. Okay, so now remember when we talk about the overlapping of orbitals, the one that can overlap would be the one that contain only the unpair, right? Therefore, in this case, we contain 2 unpair. These 2 unpair here would be the one that is going to form sigma bonds. Okay, so the reason for that is because it can, or these 2 only can overlap with another atom. So in this case, the sigma bond that is represented here would be these 2, right? Because overlap with hydrogen, and these 2 are overlap with hydrogens. Okay, so that means in this case, this represents sigma bond. This also represents sigma bond. Okay, wait, what about these 2 then? Well, these 2, they will not form sigma bond. They will not form any bonds because they already paired up. There's nothing else that can actually go in here, right? So therefore, these 2 right here, because they are already paired, this is what we call lone pair. And as you see in the structure, right, these 2 are represent this lone pair right here, right? These are the 2 lone pair. In this case, you will see that the structure, the Lewis structure that you see, it need to represent the diagram that you draw. If this result doesn't match with what you see here, that means you actually do it wrong. That's how you check your answer. Okay, so again, this result of the mixing hybridization, it needs to match with the picture of the structure that you see. Because this one can form 2 sigma bond, you already see, right? There should be 2 single bond. And because contain 2 lone pair, you already see there are 2 lone pairs. Okay, so again, you see more of this example on the homework. Okay, so make sure you understand this so that way you can go back and do the homework. All right, let's take a look at the next one. Okay, so the next one, I'm going to do the same thing so that way you can see more example, you can get a hang of it, and you can do the homework correctly. Okay, so again, in order to draw the orbital filling diagram here and assign sigma bond, pi bond, or whatever, you will first need to make sure that you determine the correct hybridization. And how you determine correct hybridization, that's when you need to make sure your Lewis structure is complete, right? So in this case, the Lewis structure still need to add the electron to them. Okay, so we still need those electrons on those 2 atoms. Okay, if you're looking at nitrogen, nitrogen contain 1, 2, 3, 3 electron region would be sp2. Okay, oxygen contain 1, 2, 3. Oxygen also contain 3 electron region as well. It would be sp2. Okay, so now to draw the diagram to represent this hybridization, it would be, I'm going to focus on nitrogen first, okay, and then we're going to look at the oxygen later. Okay, so let's take a look at nitrogen. When you are doing the hybridization, you are using the atomic orbitals of the valence electron only. Again, use only the valence electron. What do I mean by that? Well, if you're looking at nitrogen, right, so nitrogen would contain what? If you look at nitrogen, nitrogen would be He, right, and then 2s2, 2p, 3, right? Because nitrogen contains 5 valence electron. So again, we're not using this. We use only these two because these two are the valence electrons. So therefore, in this case, if when you are drawing the orbitals here, you are going to start with 2s and then 2p. Okay, because we are using only the valence electron. Okay, this valence electron of nitrogen contain 2 electron in the 2s, 3 electron in the 2p. Therefore, I'm going to add those, right? So 1, 2, 3. Okay, so those are the electron. Now we are going to hybridize, right? We are going to mix them. If we are mixing them, how many do we need to mix? Like, what are we going to combine? And that's when you are going to look at what type of hybridization that this nitrogen make, right? This nitrogen is, according to our determination earlier, this nitrogen has the sp2 hybridization. Therefore, when we draw the hybrid orbital, it needs to match this, right? So it needs to match sp2. sp2 come from, you are going to mix 1 of the s and 2 of the p. Therefore, you are going to combine only this. Okay, so 1 from the s and 2 from the p, right? So in order to make this sp2. Okay, so that means in this case, if you mix those, the result would contain 3 hybrid orbitals. So 1, 2, 3. You are going to make 3 hybrid orbitals. 1, 2, 3. These 3 hybrid orbitals is what we call sp2. Again, the reason why we are making sp2 because we originally determined that this is going to be sp2 according to the electron domains, right? Now, what about this last one that we did not use? Well, it's going to be the leftover, right? So that's what we call the unhybridized p orbitals. So this is the 2p. It did not mix, therefore the name is going to be the same. It's going to be still 2p, right? Because this is 2p. This is 2p, 2p, 2p. Just different orientation, right, along x, y, or z axis. Okay, so in this case, we're going to have 2p left over. Now, what do I do next? Well, the next thing is when you will need to fill out the number of electrons, right? So electron in the nitrogen of the valence contain 1, 2, 3, 4, 5. You are going to distribute those 5 electrons into this diagram here. Okay, so 5. So 1, 2, 3. Remember, these two are going to be very close in energy, so therefore you are going to also fill into here as well. So we fill in 1, 2, 3, 4, and then start to pair, right? So the 5th one would be here. Okay, so again, the single electron in the hybrid orbitals would represent sigma bond. Okay, the pair of electron in the hybrid orbitals would represent lone pair. Okay, and the 2p unhybridized always going to make pi bond. Therefore, in this case, if you're looking at this, you need to make sure that it's matching what we have as a structure, right? So yep, it's contain pi bond because it contain double bond, right? So double bond contain pi bond. And it's contain 2 sigma bond. Yep, that makes sense because it contain 1 sigma, which is in the double bond, and another sigma bond here. Okay, and then 1 lone pair. Where is it, the lone pair? Well, it's right here, right? That's the lone pair. Okay, so that makes sense. Again, your diagram result needs to match with the structure that we have because the diagram indicates that we have 1 lone pair, right? This is the pair electron. So we have 1 lone pair. It's contain 2 sigma, come from the hybrid orbital. So 1, 2, and then pi bond would be part of the double bond, right? So that would make sense. Okay. Now let's take a look at oxygen. Okay, so actually, since we already determined this as sp2, I would like you to actually pause the video first to make sure you truly understand this. Let's pause the video, start with the valence electron of oxygen, okay, and then do the hybridization, okay, in order to form this and see if it's matching with your prediction, right? So if all of this matching with the structure. So let's pause the video, do that, and resume it again when you finish. All right, let's check your answer. Okay, so we're looking at oxygen, right? So we are going to consider the atomic orbitals of the valence electron for the oxygen. So if you're looking at the electron configuration of oxygen, it would be helium and 2s2, 2p4, right? Because the valence are 6 valence electron total. So therefore, in order to draw the atomic orbital of the oxygen before you mix them, okay, it's going to be 2s that contain 2 electrons, and then 2p, 1, 2, 3, right? P orbital contain 3 orbitals, so it would be 4 in this. Okay, so 1, 2, 3, and 4. Okay, we are going to use these in order to make the hybrid orbitals. What type of hybrid orbital are we making? That would be the one that we determined earlier. Okay, so we are making sp2. So therefore, in this case, we are making sp2. So we're gonna mix one of the 2s and 2 of the 2p in order to make sp2. Okay, so the result of the hybrid orbital would be 1, 2, 3. You are going to make 3 hybrid orbitals, and each of these is what we call sp2, right? Together, if you show them all together, this represents different orientation. So therefore, in this case, together, you are going to make the trigonal planar, right? So that's what it means here. And what do we do with this one right here that did not undergo mixing? That would be the leftover unhybridized 2p, right? So that would be the 2p. Okay. Then the next thing is start filling the electron in here. So how many electrons do we need to fill? So 1, 2, 3, 4, 5, 6, right? We have 6 electrons. So you are going to fill 1, 2, 3, go all the way to 2p, 4, 5, and 6. Again, these two energies are very close to each other. So that's why we are able to go up to the 2p. Okay, so now you are going to assign the type of bonds that go in here, right? So pretty much those that contain pair of the electron already, right? So this would represent lone pair. Okay, so this is lone pair. This is also lone pairs. Okay, so we have 2 lone pairs. And the unpaired electron in the hybrid orbitals, this represents sigma bond. And the unpaired electron in the unhybridized orbitals is going to represent pi bond. Okay, so make sure that these have to match with what we have. If this is not matching with the structure that we have, it just means that we are doing this incorrectly. Okay, so if you consider oxygen here, this oxygen contains 2 lone pairs. 1, 2, right? So exactly what we have is contain as double bond. Double bond contain 1 sigma bond plus 1 pi bond, which is exactly what we have here, right? We have sigma bond and we have pi bond. So that means in this case, our diagram is correct. Okay. So the review of this lecture video again, these are the type of hybridization that you will need to know, especially the first 3. This one you will need to be able to draw a diagram. Okay. So the homework associated with this would be paper homework chapter 6.3 to 6.4, which is going to be this part right here for this video. Okay, so you already see the different shape of the orbitals, right? So you should be able to answer that. And number 4 and 5 is going to be similar to what I showed you earlier, right? You will need to first determine the correct Lewis structure of this first by complete them with the correct lone pairs. Okay, by using the number of correct lone pairs, you should be able to determine the electron domain geometry, right? So the electron domains or the electron domain geometry will tell you about the hybridization. Okay, once you know the hybridization of this, then you should be able to use the atomic orbitals of each of these atoms, right, to start the way that we did earlier and mix them. Okay. And make sure that your result here needs to match with the structure that you have. Okay. Now number 6 here is similar to what we did earlier as well. So you are pretty much going to determine the hybridization of carbon. So since all of this carbon gonna have the same type of hybridization, you just need to answer me one. Okay. This number of sigma bond and pi bond would be the total that you see in this molecule. Same thing for this as well, right? You are going to determine the hybridization of each of those. Okay, so that would be part of the paper homework 6.3.